for the opportunity to talk to you today. I want to talk about this work, which is hopefully going to come out soon. We're just, I think, in the final stages of revisions. And looking at a global discrepancy in atmospheric water vapor trends between models and observations. So I want to acknowledge all my collaborators listed here, and also funding from the NOAA MAT program and from NSF to NCAR as well. So I just want to start by giving you a couple of motivations of why we should care about what atmospheric water vapor has been doing historically. And one of these is on my title slide here. This is a picture that was taken from NCAR's Mesa Lab, where I work. This is the Marshall Fire that happened at the end of 2021, and it was the most destructive wildfire in Colorado history. And I know that in Australia, of course, you've had a lot of wildfires as well. It has been really dry in the US Southwest, and so we've had some pretty extreme wildfire seasons. And this is just another picture that I took myself. This was just a few months after the Marshall Fire. This is a fire that became known as the NCAR fire. This is NCAR's Mesa Lab here, if you're not familiar with it. The wind was blowing in the other direction, so NCAR is still standing. But, we have had just these very extreme wildfire seasons kind of all over the world, really. And of course, there are many reasons why fires happen, but one is that there are these very close links between atmospheric vapor pressure deficit and wildfire. So it matters how hot is the atmosphere and how dry is the atmosphere. So vapor pressure deficit it's the difference between the saturation vapor pressure, which depends on temperature, and then the actual vapor pressure, which is just how much water vapor there is in the atmosphere. And so here is just an observation-based analysis. This is over the American West, and it's showing this link between vapor pressure deficit and burned area in each of the fire seasons. And this is not a linear scale. This is an exponential relationship. So what we're seeing in many regions is increases in vapor pressure deficit, which is leading to increased wildfire danger. And of course, a large part of that is temperature, but it also matters what the actual water vapor content of the atmosphere is as well. Another reason is that we just kind of want to know how is the hydroclimate going to change in the future. And of course, we use our Earth system models to try and address that question. And that relies on getting many processes right, many of which we haven't really observed, at least not globally, and not on the kind of multi-decadal timescales that we need to have been. So of course, we have precipitation observations, but most of these other things are really not very well observed. But we do have observations of near surface humidity. And so you could kind of, in some sense, think of that as maybe telling us about how all of these processes together are evolving in time. And if we see something going wrong with humidity, then we have to worry, are we getting something wrong in these processes that matter for the hydroclimate in general? So I'm going to start off here with a case study of the US Southwest, but I'll get to the global picture in a minute and show you historical trends in vapor pressure deficit divided up into the saturation vapor pressure part, which depends on temperature, and then the actual vapor pressure part, which is how much water vapor there is in the atmosphere. So we're going to average over this 6-state region of the US Southwest, and I'll show you annual mean trends from 1980 to 2020. So what you're going to see here in this figure on the x-axis is going to be the actual vapor pressure trends. So that's how much water vapor there is in the atmosphere. And on the y-axis is going to be the saturation vapor pressure trend, which is the part that depends on temperature. And then these contours here are going to tell you the value of the vapor pressure deficit, which is the difference between these two things. So to begin with, here is ERA 5 reanalysis trends. And so what you see in ERA 5 is that over the Southwest, there's been an increase in the saturation vapor pressure because it's warmed. But we've also had this pretty big decline in the actual vapor pressure. And this is not very sensitive to ending in 2020. 2020 was a very extreme drought year in the US Southwest. But we see a similar picture if you end in 2019 as well. Now, here's what the trends in each of the individual members from all of the different CMIP6 models look like. So each model is a different color. And you can see that for saturation vapor pressure, the temperature part, the reanalysis here, it lies pretty squarely within this model distribution. But for the actual vapor pressure, it does not at all. And so the models kind of overwhelmingly suggest that we should have seen an increase in vapor pressure. But in the ERA 5 reanalysis here, we see a decline. And so when you look at vapor pressure deficit, we do have some model members that show you as big of an increase in vapor pressure deficit as what we've seen in the reanalysis here, but for pretty different reasons. They're having more warming, which is compensating for not having this decline in the amount of water vapor in the atmosphere. And I'm sure you're interested in what ACCESS looks like. So these are the ACCESS model points. So they lie pretty squarely within the model distribution. Of course, a large part of the spread here then is internal variability. So here's also one single model large ensemble. So this is the model developed NCAR CSM2. This is a 100-member ensemble, and you see the same picture here. The CSM2 members overwhelmingly are all positive in their vapor pressure trends, coming nowhere close to what has actually been seen in the reanalysis. And then in our model, we've also extended our AMIP type simulations out to 2020. It's hard to look at this in the CMIP 6 runs because they only go to 2014, although I'll show you some more later on. But this is what our AMIP type simulations, we call them GOGA runs for global ocean, global atmosphere. That's what they look like. And so they get you a little closer to the reanalysis, but they certainly don't get you to this big vapor pressure decline that we've seen. So our models seem to come nowhere close to simulating this negative vapor pressure trend that we've seen in the reanalysis here over the US Southwest. This is just showing you the vertical structure of specific humidity trends over the Southwest. This is on terrain following coordinates, so on sigma coordinates, and then averaging over the Southwest states. And here are all the members from the CSM2 large ensemble. And then this is ERA 5. And so if we trust the vertical profiles here in ERA 5, you see that the discrepancy is really largest at the surface, but it's kind of there throughout the depth of the lower troposphere here as well. So of course, a big question is, do we really trust ERA 5 vapor pressure trends? I'd say it's our latest and greatest reanalysis. But of course, it's not going to be perfect. And so here I'm going to try to convince you that I think we can trust ERA 5. So here's a map of the trends in vapor pressure for ERA 5. And you can see that there's this broad region over the Southwest where we've had this decline. And this is what the raw ISD stations look like. So these are not independent of one another. ERA 5 assimilates station-based humidity measurements, but it's reassuring that you see the same thing in the raw station data. So we at least know that it's not some spurious trend in the reanalysis as you start to assimilate different observations at different times, or some issue in the underlying model of ERA 5, because we see the same thing in the stations. Of course, we don't know for sure we can trust the stations, but that's as close as we have to reality. And so without any reason to distrust them at this point, I'm kind of trusting them. I'm just showing you here the time series of annual mean vapor pressure over the Southwest. You've got the model ensemble means here for CMIP 6 and the large ensemble, and then the range that encompasses 95% of the members. This is the time series for ERA 5. This is for the ISD stations in the gray. And in the light gray here, I'm showing you the homogenized HAD-ISDH dataset from the UK Met Office, which is based on ISD, but they've applied some different procedures and some different homogenizations. And you can see that they all kind of agree. And also there's not really a jump in any particular point in the record. It's a pretty steady decline. So taking all that together, I'm kind of going to assume that we can trust the station data. And this is a real trend, but of course that's, new information could come along that could make us question that for sure. So here in the blue, I'm just showing you what you get if you prescribe the observation-based sea surface temperatures, and that definitely limits the increase in vapor pressure that you see, particularly during the early 21st century when we have the global warming hiatus period. But after that, the AMIP models kind of catch up with the couple models, and they're also also distinct from the observations. Now, the Southwest has experienced a pretty big precipitation decline since 1980, so we could kind of reasonably expect maybe this vapor pressure decline is related to that. And so here what I'm showing you now across the models, we've got CMIP6 on the left and we've got the CSM2 simulations on the right. What we've got on the x-axis is the precipitation trend over the Southwest, and on the y-axis is the vapor pressure trend. So we learn a couple of things here. One is that the vapor pressure trend is correlated with precipitation trend across the model members. So if you have a member that has a bigger increase in precipitation, in this case in the large ensemble, that's just due to internal variability, you end up with a bigger increase in vapor pressure, and vice versa. But we also see that all of these model points are kind of offset in the vertical to positive values. So even if you have a zero precipitation trend in a region, you see a rise in vapor pressure, and that's because there's a thermodynamic influence of greenhouse gas-driven warming on atmospheric water vapor. So a warmer atmosphere can hold more moisture. Following the Clausius-Clapeyron relationship, if you have water available, you'd expect water vapor would increase with warming. But here is where the observation-based data sets sit. So we've got 3 different precipitation data sets here, and we've got the ERA 5 and the ISD stations for the vapor pressure. And what you see is that indeed the Southwest has experienced a pretty large precipitation decline, but it doesn't lie outside of the model distribution. The models are definitely capable of producing as large a decline in precipitation. But the vapor pressure decline kind of is offset from what we would expect, even given that precipitation trend. So this kind of raises 3 possibilities here. One is, are we kind of getting this relationship between precipitation trend and vapor pressure trend wrong? Should it actually be steeper in the models so that with this precipitation decline, we can have a bigger vapor pressure decline? Another possibility is, are we kind of getting this forced thermodynamic rise in water vapor that shifts all these model points up in the y-axis? Is that too large in the model? Should it really be closer to 0 so that this relationship can then encompass the observations? A third possibility is, are we kind of missing some additional variability in vapor pressure that's unrelated to precipitation? Should our residuals around this relationship, should they be much more spread out so that they can encompass the observations? So to try and kind of distinguish between those 3 possibilities, I'm going to now take a step back and look at what is happening to vapor pressure trends globally. So here's the global trends in vapor pressure. We've got ERA 5 on the left, and then the stations on the right. And there's pretty good agreement where we have stations. Of course, we have vast areas of the globe where we don't have a lot of station data. And then what I'm showing you here in gray are regions where the ERA 5 trend lies within the spread of the CMIP6 models. So we have a number of regions now that kind of jump out as being distinct from the model distribution. It's not just the Southwest. We have many other regions, including parts of Australia, where ERA 5 shows a relatively more negative trend in vapor pressure than what the models seem to be capable of producing. But we can also account for what precipitation has been doing locally. So precipitation in reality will have been doing all sorts of things locally, probably as a large part due to internal variability, and we can account for that. So I'll just kind of walk you through how we'll account for that, showing you a point here over South Africa. So here I'm again, just like we saw for the Southwest, showing you the relationship between vapor pressure trend and precipitation trend. And here's the observation-based data. So this is outside of the model distribution, whatever way you look at it. But suppose the observations were here. If we just asked, is this outside of the model distribution when it comes to the vapor pressure trend, we'd say no, because there are members that give you as big a decline there. But if we account for the fact that it's getting this decline in vapor pressure while also having this particular precipitation trend, we'd say that yes, this does lie outside the model distribution. So what we're going to do is kind of take all of the CMIP6 models and members and calculate the linear relationship between the vapor pressure trend and the precipitation trend. Calculate the residuals from that relationship and their standard deviation, and then use those to put on a kind of plus or minus 2 standard deviation range around this regression line. And then we're going to, instead of just looking at the vapor pressure trend, look at the difference from what you would predict based on this relationship and ask, does it lie outside of this gray shaded region? And so with this kind of calculation, if our observations were here, we would now say, yes, this does lie outside of this distribution. So here's what you get in the CMIP6 models when you account for precipitation trends in this way. And now we have many more regions that kind of jump out as being distinct from the model distribution, including a much larger fraction of Australia. Almost all of these regions are negative in the sense that the vapor pressure trend is relatively negative compared to what the models suggest it should be. There's just a couple of regions where the opposite is true. Now, the regions that we see here are not really randomly distributed. If we look at the kind of divide up the planet into climatological aridity zones based on just a standard aridity index, you can see that the vast majority of regions where we see this discrepancy are regions that are classed as arid or semi-arid regions of the world. And we can kind of quantify that a little more in this way. So here, what I'm going to show you are trends in specific humidity expressed as a percentage of the 1980 to 1990 climatology and normalized by land area average near surface air temperature change. So now we're looking at trends in percent per Kelvin. So we can compare with kind of Clausius-Clapeyron scaling estimates when we look at it that way. So what I've done here is kind of taken all of the grid points of the planet and binned them just over land and binned them into 30 equal area bins on the y-axis according to their climatological aridity. So we've got the most humid regions on the top and the most arid regions on the bottom. And then for each aridity bin, we've binned into 15 equal area bins according to the precipitation trend. So we've got the most negative precipitation trend on the left, the most positive on the right, and then near zero trend at the 50th precipitation percentile. And then these white hatched box bins are their bins where the trend is between 6.5 and 7.5% per Kelvin. So this is kind of around our 7% per Kelvin trend we'd expect based on Clausius-Clapeyron scaling. So these are the humid regions. Between these dashed lines are the arid and semi-arid regions, and then we've got the hyper-arid regions down below. So this is ERA 5. This is the CMIP6 ensemble mean. And what you see here is that the CMIP6 models are very closely following Clausius-Clapeyron scaling, regardless of the climatological aridity. So even in these arid and semi-arid regions, if you have near zero precipitation trend, you've got about a 7% per Kelvin rise in humidity. This is the difference between them, and now stippling is showing you regions where ERA 5 lies within the distribution of the CMIP6 models. So what you see is that where we see this discrepancy is kind of overwhelmingly within these dashed black lines in the arid and semi-arid regions of the world. So ERA 5 is showing reduced specific humidity trends compared to the models in arid and semi-arid regions, regardless of what precipitation has been doing. This is another way of looking at it. So what I'm showing you here is still specific humidity trends in percent per Kelvin, still binning on the y-axis according to the climatological aridity. But now I'm taking the 12 months of the year and ordering them from the most arid on the left to the most humid on the right. So this is ERA 5. And then when you do this, you kind of average out your precipitation trends in each bin, roughly. That's what you get in the CMIP6 models. And then this is what the difference between them looks like. So when we look at it this way, we can actually also see that there are some discrepancies in the humid regions, but just in the most arid months of the year. So it doesn't kind of come out when you look at the annual mean. So ERA 5 lies outside the model distribution during the most arid months, also in the humid regions. And it's during these times where the kind of aridity index in those regions gets into the realms of what we see in the arid and semi-arid regions kind of throughout most of the year. So there are pretty close ties between where and when we see this discrepancy in humidity trends and the climatological aridity, both spatially and seasonally as well. So now I'm just going to finish up by focusing on regions that are arid and semi-arid region of the world, looking at the annual mean. And so here's the joint probability distribution of specific humidity trend versus precipitation trend in the CMIP6 models. This is just the values you get averaging over precipitation bins of this width. And then this is a 7% per Kelvin trend line. So what you see in the models is very close to Clausius-Clapeyron scaling. This locations where you have a positive precipitation trend, it gets slightly higher than that. And where you have a negative precipitation trend, it gets slightly lower. So this is pretty analogous to what I showed you over the Southwest across members, but now we're looking at it across space. And because we're looking at cross space, we can now also look at this in the observation-based data. And this is what we get in the observation-based data. And what you see is that the observation-based distribution is offset from the model distribution at all precipitation trends. So if you remember back when we were just looking at the Southwest, I kind of wanted to distinguish between these three possibilities. And looking across space, I think we can now do that. And we can see that the primary difference here is the offset in the vertical, that in the models, we see this thermodynamic rise in water vapor that shifts the whole distribution to positive values. And in reality, that just hasn't happened. This is a very distinct difference between the models. I just wanted to show you what every individual model looks like in terms of the distribution of specific humidity trends when you average over regions that have a small precipitation trend in this region here. You can see that it's really a pretty drastic difference in the distribution of specific humidity trends in each of the members of each of the models. So there have been previous studies that they've recognized that relative humidity has been declining more in observations than in models, looking across kind of large geographical regions. But here, I think what we're finding is that this discrepancy is very closely tied to climatological aridity. And when you just focus in on the arid and semi-arid regions of the world, the discrepancy becomes very severe to the point that we actually don't really see any thermodynamic rise in atmospheric water vapor over those regions that the model suggests should have happened. So something is wrong, and this could have potentially severe implications for our climate projections moving forward. Just want to kind of finish up with this summary time series here. So I'm just showing you time series averaged over all arid and semi-arid regions of the world. This is temperature over those regions. This is temperature over the oceans, specific humidity over the arid and semi-arid regions, and then relative humidity. So here you see the models, the coupled models. This is what you get in the AMIP simulations. So certainly AMIP simulations kind of reduce the warming of the oceans in the hiatus period, and associated with that, you kind of have a stalling of humidity rise, but then it continues after that. And then this is what has been happening in the observation-based data. So even though we're getting our temperature trends pretty close over these regions, the specific humidity has not been rising. And as a result, the relative humidity has been declining a lot more than the models suggest it should have. So I don't know the answer to what is going wrong. We're hopefully about to start moving forward with this to try and figure it out. And I've listed a bunch of suggestions here, which I won't go into in detail, but my feeling is that the most likely thing is that because it's so focused on arid and semi-arid regions of the world, that the most likely thing is the availability of water from the land surface. But there's still a possibility that it's some kind of a transport issue. One other thing to mention is that just because we're seeing it in the arid and semi-arid regions doesn't necessarily have to mean that it's a problem that's only happening there. I think it makes sense that we might only see this in the arid and semi-arid regions when you think of the kind of standard relationship between evaporative fraction and soil moisture. When you have enough soil moisture, it doesn't really matter if you decline as to what happens to evaporation. But at a certain point, a decline in soil moisture can lead to a big decline in evaporative fraction. And so it could just be that in these arid and semi-arid regions that are kind of in the realms of this drop off here, that we're starting to really see it happening. But that kind of remains to be understood. So I think it's a challenge to solve this problem. Many of the quantities are not really observed properly. A couple of approaches we're planning to take is some perturbed physics runs to see what does it take to get this decline. And then also to try and see, can we see anything analogous happening on short time scales as well, where we do have some more observations. So to summarize, a warmer atmosphere holds more moisture. And so with warming, we expect an increase in atmospheric water vapor. In our models do this. They show rise that's very close to Clausius-Clapeyron scaling, even in dry regions. Assuming we can trust the station-based humidity measurements and therefore EUR5, this rise in atmospheric water vapor has not happened in reality over arid and semi-arid regions, which points towards a misrepresentation of some process or processes that are of relevance to hydroclimate in our Earth system models. And I think we need to try and resolve this to improve the credibility of our projections. So that's all I have. I'll be happy to take any questions or any suggestions of what you might think might be going wrong to explain this. Thanks.
Thanks so much, Isla, for the really interesting talk. Do we have any questions? Steve?
Hi, Isla. Isla, Steve Sherwood here from NSW. I thought that was a really great study. I love how you forensically dug in there to try to figure out what the pattern, figure out what's going on. I do have one alternative suggestion, though. Having tried to homogenize climate data myself, having given up on humidity because it's too hard, one of the problems with hygristors is that they all tend to go bad at low relative humidity. So the old wet bulb thermometers, the cloth has a tendency to dry out when relative humidity is low. Passive hygristors also tend to lose sensitivity to low relative humidity. If that has improved over time, it could potentially account for all the things that you've shown. And so what I'm wondering is whether you looked at the distributions of relative humidity over time to see if there were any evidence of, say, the tail dry in getting locked off at some point when they upgraded sensors, that sort of thing.
Could you hear the question, Isla?
Yes. Yeah. Yeah, it's a good point. It's also, yeah, one that the reviewers raised as well. Yeah, it's definitely possible. I think I haven't looked in detail in the way you suggested. It's definitely on my agenda to start looking more at the distribution and higher frequencies of what's happening with the humidity. Yeah, I mean, the only arguments we can make at this point is that we see the same thing in data sets where they have tried to account for that with homogenizing in the HAD-ISDH data set. Also, it happens, everywhere it kind of agrees. And I know that, I mean, I don't think everywhere it changes their sensors all at the same time. So we need to explain a global improvement that's kind of happening gradually everywhere, which may be the case. I'm certainly not an expert on these kinds of observations. But my feeling is that those things are all kind of pointing it toward it being a real signal, but I will definitely look at in more detail in the distribution in the way you suggested.
I have a brief question, Isla. I was wondering if you could comment a little bit more on this aspect of precipitation intermittency. Whether, like, if you're looking at sort of really extended dry periods followed by extended wet periods a bit more, that could sort of make locations behave more like an arid or wet region. Whether you were able to kind of detect any of those effects in the models.
Yeah, so definitely one thing, I mean, I think we know that models don't get precipitation intermittency correct. More drizzling, which you'd think would make them have more water available in general at the land surface, less running off. The only things I have to say about it is that we have looked at offline land model simulations that are forced with observation-based precipitation, and that they look very similar in terms of what soil moisture and evaporation are doing. So I feel like if it was just going to be the issue related to precipitation intermittency, I think we need more than that. I think we need the land model to be doing something wrong with that to explain those offline land model simulations. But I definitely want to look more at like higher frequency dry periods. I know that there's been some work from the Australian group and also from a group at Stanford that it kind of show the opposite from what I expect on high frequencies, is that when you get into droughts, models are less likely to show increases in evaporation, which kind of goes against what I would expect. So I think there's definitely work to be done looking at high frequencies and see if we can see analogous things there.
Okay, thank you so much, Isla. So if there's no more questions, can we just thank Isla once more?